The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Jonathan sent the email. If you have questions, you still need a clarification, you send him. But say we still expect you decide to redo it, you should do it yourself. There are no discussions. You can go back and look at any books, but you do it yourself. Okay? Any clarification in it? Okay. Then let's come back. This is the chapter I spend most time in terms of per chapter so far. We're really talking about the transport law, and the content we talked is best applied to ballistic transport, meaning there's no scattering. You can still treat it with scattering, but let's say right now what we're saying is if I want to know the transport between any 2 points, right? And then now the transmittance. So we learned how to calculate transmittance of an interface and how transmittance of film, multi-layer, vacuums, tunneling, all those. In theory now, you can at least say you're not afraid of dealing with this type of problems. So if you know the transmittance and the left flux, whatever flux, here I'm doing the heat flux. So h bar omega is energy. And I'm doing 1 to 2, mass 2 to 1. But at the end, apply the principle of detailed balance, which is essentially second law. It says at the equilibrium, the lead flux must be 0. And otherwise, you have creating imbalance. Heat can go spontaneously from hot and cold sides. So that's not valid, and that's the principle of detailed balance. So essentially, you can say when we want to calculate flux is the velocity, transmittance, the quantity that transported here is 1 mole, right, quantum state, and then the distribution function difference. Each state, how many particles we have at the corresponding temperature, chemical potential, and of course the energy. So the detailed balance really saved us from calculating both sides, because say you can take any of the sides and do your calculation as long as you know the transmittance from that starting side to the other side or other point. And I emphasize at the end of last lecture, those kind of transport is a high long equilibrium. So it's actually hard to really define a quantity that we're used to. Even temperature, chemical potential, those are all thermodynamic quantities. And the example we spent some time to explain is thermal boundary resistance. When I have acoustic wave comes toward the interface, and on this side, this is my, in fact, this is my TE1, the corresponding distribution of photons coming from this side, and reflected and transmitted, right? And on the other side, I have the incoming with the characteristic temperature at TE2, reflected and transmitted. So locally, I do not have, at the interface, on each side of interface, I do not have equilibrium. And when I force my temperature definition, is this temperature, the local energy, is not actually just a TE1 characteristics, but also transmission of TE2 characteristics. So if you redefine a local temperature, or if you do charge transfer, a local chemical potential, electrochemical potential, right? It's not the incoming one, and you have to recalculate what's the local. For example, if I want to force temperature, to be equivalent measure of a local energy density, I will define the local temperature based on local energy density that will give me a different temperature than this one. So those are highly long equilibrium process. I think the best way you understand this is taking the undergraduate problem of black body radiation, right? If I have two black surfaces, and this is a T1, and this is a T2, and now if you look at the inside, I have photons coming from 1 to 2, and this has a characteristic of temperature 1. And then I have photon going the other side and have a characteristic of temperature 2, right? And then you ask, what's the photon temperature? You say, there's no equilibrium, clearly, right? You can't define a photon temperature inside. And now you say, OK, I imagine I have a detector with two faces. Both sides is black. So I have a small detector with both sides black. On one side, it absorbs the temperature heat from with the temperature T1. The other side with the temperature T2. And you have an equilibrium temperature here because the absorber thermalized, right? There's two temperature, two group of photons. And that temperature is flat inside. It's because there's no change. It depends on going from one side to the other. There's no change. So if you say, OK, define the photon conductance, if I define based on the photon temperature here at the two sides, you know there's no delta T, and your conductance is infinite. But if I define based on the temperature of the solid, I can't measure this easily. I don't have that detector, right? But I can define, if I put my thermocouple to measure two solid surfaces, solid object, black body, I'll measure T1, I'll measure T2. My thermocouple is not measuring the photon temperature. My thermocouple is measuring the solid temperature. In fact, my thermocouple is measuring the photon temperature. So you actually fooled in this case, right? But that's what in your engineering calculation, that's the definition you'll be using. So this is the temperature you'll be using. You're using the solid temperature there. So I give another example where, say, people measure the conductance of a wire, electric conductance, right? They put a two metal probe. For example, you do a carbon nanotube, right? They put a two big electrode. You measure voltage here. That's like you're measuring these two solid temperature. You can't measure the electron chemical potential exactly at the contact. You don't have, say, probe that easily measure that local voltage. If you measure that local voltage, again, the electron in the ballistic regime, there's no voltage drop. You should get an infinite conductance. OK, so this definition dependent. When you do your experiment, you need to know what they're comparing to. Don't compare orange with apples. OK? So with this, basically, you can really, if you do nanoscale transport, this could be a foundation to understand a lot of papers in literature. People are studying different kind of nanoscale transport problems. Right? We talked about conductance and many other examples. So just to take the carbon nanotube, right? And if you write down, say, the electric conductivity, so there is this universal conductance. And it turns out that universal conductance for one-dimensional object, it doesn't depend on the material. And the conductance G per mode, per quantum channel, quantum state, right, is E squared h bar. Let me check whether there's a factor of 2. E squared pi h bar. Right? So if you substitute a number, this conductance or equivalent resistance, which is the inverse of the conductance, is 12265 ohm. Okay. So through each channel, you add another channel. You have two parallel channels. The conductance doubles, resistance reduced by half. Right? The quantum states. So people have in the past measured. In fact, there was an experiment doing, say, various quantum transport at particularly low temperatures. And this is electrical. And you can do thermal. Right? If I have two temperature difference between 2 points, and the thermal conductance for one-dimensional object is pi kb t, kb squared t, and divide by 6 h bar. Okay, and this one, so it's not. This is again universal because it doesn't have a material property there, right? And if you plug in your number conductance here, I get about this is 10 to the 12th times T and watt meter square Kelvin. So this number will be interesting for some of my students doing the interface resistance, right? It's we know they oh, this is positive 12. No, well, let me see. Negative 12. Wait, I have some number problem. Pi kbt square, kb 46, 10 to the minus 12, t, and watt meter square. So the no, I think I have some. I have to check this number. It doesn't look right because G typically is 10 to the 9th. This is minus 12. So maybe I'll check. Okay, I don't know where it's wrong now. Okay, so that's the universal conductance. And if we do, for example, we do near field, I have two plates, right? And I have typically the wave comes in and has reflection and has transmission, right? We said that when the two surfaces are brought close by, you have a tunneling phenomena, and again, with that you can calculate transmittance, and you do your integration over all states, you can get the increased heat transfer due to the tunneling. Or if you're interested in electrical charge tunneling, all those can be done now. So I think it's I encourage now you can look at literature. People study all this different, say the nanostructure, conductance, transport, and this is very often discussed. What I have not finished is what's the velocity. It turns out this one is actually one that we asked at the beginning, how fast the particle really travels, right? So let's discuss this velocity, group velocity. And this is a concept sometimes very hard to appreciate, to understand. What is group velocity, right? So definition-wise, it will be relatively easy. But why we say the group velocity is typically when we calculate the charge, the heat, that's the velocity I do in my Vx here, for example. Why I use group velocity? So first, say, let me take a picture of photon dispersion, where in specific direction I have k, I have omega, and I have acoustic photon, one branch only. I'm looking at it, and the group velocity is tangent of every point, and that's the group velocity. And it's this velocity we use when we substitute into the transport. That's how fast, how much energy, say, a photon will carry at that specific mode frequency, right? Why I use that velocity? And first, let's look at a wave, because I've been talking about plane wave representation, right? So a wave that I usually use either vector or scalar. Now I just write a simple scalar wave is minus I omega t minus kx, right? I'm assuming that k is in the x direction. Simple. And this is the plane wave representation I have, right? What's the origin of my time? What's the end of the time here for a true plane wave? That's minus infinite to plus infinite. That's a true plane wave, right? There's no ending point, okay? Anytime I have an ending point, I don't just have one single frequency there. So, for example, if I have a periodic signal, I can say this is omega 0, but it only has a finite time span, right? Let's say t0. It only has a finite time span. And normally you say, OK, I have a periodic signal. But mathematically, that's not quite correct, right? Because this signal does not go from minus infinite to plus infinite. And if I have periodic signal over only segment of time or length, I can do Fourier series, right? So you can do your Fourier analysis, and you see the real frequency of this wave is not, let's say, here the omega 0 is my fundamental frequency of this wave, right? And then I have omega 0, I have harmonics. Omega 0 will be my highest modes, and 2, 0, and so, right? Different frequency around the central frequency. That's when I do the Fourier analysis. OK. So now, because of this, because in a solid or whatever, there's never really a wave that goes from minus infinite to plus infinite. The generators, for example, the atomic vibration, or electron transition from high energy to low energy, they only span a certain amount of time, right? All the event only span a certain amount of time. So I have to consider what happens when the actual event is, for example, happening at a short time, right? And in this case, I have multiple frequencies, not just one single frequency. So if I have multiple frequency, let's look at the simplest. If I just have two frequencies, what happens, right? Let's say one frequency is omega 0 plus delta omega. And correspondingly, I have k0 plus delta k, right? Because it's not linear, so I have omega 0 minus delta omega and k0 minus delta k. So those are two different waves with slightly different. They all center at the omega 0, but they are small spreading, right? Delta omega and delta k. And now I have really what's propagating are this simultaneously two waves I generated, and the superposition of these two waves, right? So if I look at the superimposed wave, A, I'm assuming they are same amplitude just to make our life simpler, and minus I omega 0 plus delta omega t minus k plus delta k x, k0, and plus the other frequency, and the wave vector is minus I omega 0 minus delta omega t minus k0 minus delta k x. And I have the superposition of this real signal that propagating in the media because it has two waves in the signal. And when I add this up, you have a central frequency, omega k0 I can pull out. Then I have a plus term, a minus term in the exponent. So you do your algebra, what you'll get is 2a cosine delta omega times t delta k times x, and then exponential minus I omega 0t minus k 0x. So this is the result when I have two waves that with a small separation in frequency and wave vector. And you look at this now, what's propagating. Here I have a high say frequency omega 0, k0, central one. Here I have another cosine that modulate this frequency, right? So what I really have is a cosine signal that's a delta omega delta k, so which is slower typically. And then this is the amplitude of the, right? So at the center I have omega 0, k0 modulated. So this is the FM signal. Is it AM or FM? AM signal. You're modulating the amplitude of the central frequency, right? So now this is a, so now I have the outer envelope is cosine omega t minus kx. Now if you think about what energy, right, say the Poynting vector. For example, when I think about electromagnetic wave, my Poynting vector is E cross H, right? And of course, I have 1/2 real part of that. Now, if I have this term inside, E cross H, right? E has this term, H complex conjugate also has this term, but as a plus. You know that this term actually drop out when you do E cross H. So what is really then the energy is actually the front term here. So what energy is propagating is like, in this case, is a slower packet propagating. That's a wave packet. And the speed of this propagation, now if I look at this factor there, is dx dt. So the dx dt is delta omega delta k. So this is actually what the propagation, this wave packet is propagating at this speed, new speed there. And this speed in the limit of very narrow delta omega delta k, I have a derivative, right? So this is equals d omega dk, and this is my Vg group velocity. That's why I'm doing the group velocity, and when I do transport, I use V, the group velocity. The phase velocity is omega over k. That's this triangle here. That's the phase velocity. And in fact, if you go to check your density of states, when you calculate density of states, you involve phase velocity. You involve both phase velocity and group velocity. Okay? But so when I do transport, when I think about how fast the particle or energy is going from one place to other, the wave packet, and I should use the group velocity for the actual transport speed. And when I calculate the density, when I convert these modes into density through density of states, I should be careful. Some is group velocity, some is the phase velocity. And of course, this is only one direction. And in three directions, in general, so the group velocity is a vector. Right? So this one is, for example, if you do Cartesian coordinate for k space, is d omega dkx, kx, and d omega dky, ky, and d omega dkz, kz. So that's a general group velocity. And with that, you can say, now if I go back to photons, right? And this is the, when I have the optical photon, acoustic photon, right? If you look at the group velocity, very small k, this was the tangent here, is much larger. Then at the end of the k, zone boundary, k typically is 0, flat. So here is the speed of sound that you can measure. And here at zone boundary, group velocity typically 0. So the acoustic photon group velocity is changing. Optical photon, the group velocity is typically very small, even though the phase velocity is very high, omega over k, right? Omega is very large. Phase velocity is large, but group velocity is very small. And when you do specific heat, it turns out the simple Debye model or plus Einstein model is fine. But when you do transport, this velocity becomes more important. So even though most models in literature, and in fact 90% of those papers you check now nowadays, we typically simplify the Debye model or Einstein model. We do heat transfer, thermal conductivity. But that will typically lead to very different results from reality because of the use of the group velocity there, a big major factor. And this is the case of photon. And you can also say, think about electron. So for example, I have electron. This is the energy. This is the k. That's typical dispersion, right? And so at the center, the minimum, the group velocity is 0. This is because it's a parabolic band, right? We said some electron, in fact, in the problem in the midterm, we see some of this graphene they have, but as a linear dispersion. So at the k equals 0, the velocity is not 0. But say most time this is 0 and velocity is 0. So if you think about the parabolic band, the group velocity, right? Let's say here kx is d omega. Omega is e over h bar, right? That's omega. And d kx, let's say in the x direction. And e, if it's a parabolic band, right? Then you can say it's h bar k x over m. So this is p over m, momentum divided mass. That's consistent when we have in the classical limit, right? So, but on the other hand, if you say, okay, my h e equals h bar square k square over 2m, right? So this is a typical parabolic band, right? And if I just use the phase velocity of this, I will not get the same as group velocity. So group velocity is like my speed of the free particle there, because the phase velocity you get a factor of 2 difference. But there are some interesting cases. This is actually, we always say most of the time that group velocity is the one you calculate transport. There are trickier cases where this becomes very, this is actually not right. And if you check the literature over probably last 15 years, there are actually discussion. People will say, well, some of this goes over the speed of light, right? And in fact, if you look at the optical constant, we know that the speed of light in a media is c0 over n, right? This is the phase velocity. And it turns out that you check the optical constant of some media refractive index, real part, this is n, this is omega. And so at some omega 0, you may have, this is a 1. This is a 1. And the sum of this omega look like this. Refractive index, real part. So what happens is here, of course, n is less than 1. So the phase velocity is much larger than the speed of light. But that's fine. You'll say, OK, that's not the energy velocity. OK? So you're still comfortable. But then if you go to take the derivative of dn say omega, you find that even the group velocity in this region could be larger than 1. So you run into, are you violating Einstein's relativity principle? Right? And the reason then is that in this case, it's actually not the group velocity, it's the energy velocity. Right? And when this varies very rapidly, when this omega 0 or omega varies, or k varies very rapidly, and those quantities is a strong function of omega k, so you cannot pull out and do the analysis we do here. So in that case, there is actually a so-called signal velocity. And about 15 or I remember probably in the 90s, there are actually some sensation. People actually measure some of the signal first reach beyond the speed of light. Anything beyond the speed of light, Einstein says Einstein still valid, right? Then say it's the people who do the work will say this is not a violation of Einstein's relativity principle, because this is only the first part of the signal. The signal has not completely gone through it. So your light, even though the front of that signal comes, but not all the information has to be transferred. So you're still not violating the Einstein principle, but there are a lot of news coverage all that time. And so anyway, that's a sidetrack. So that's why when we do the calculation, we will use the group velocity. So we have now say answered pretty much all the questions, right? Say how fast, that's group velocity. Say how many, right? Density of states. And then each state, the distribution function, right? And so with those, say how far, and in certain case, those transmission tells us how much is going forward, how much is backward. And what we're going next is here, all the discussion is based on the wave picture, right? But if you think about your mechanical engineer, none of the equations you learned so far was based on wave picture, right? How we go from that wave to completely ignore the wave, to treat them as particles. So this is another very, very deep subject, okay? And it's one that people are still doing a lot of research on. And I'm going to give you my best shot at making a transition of forgetting those phase of the wave and going to the particle, right? So one of my objective is for you to say when you should get worried, right? At which domain you should be worried about wave effects, classical size effect, and you feel comfortable using your continuum equations. So that's one of my objective. And now I'm shooting at, after group velocity, is a wave to particle transition. And this is where I say we're still, for example, even now, we're trying to write a good paper on it. And there are many, I say, concept that I learned before. I had to revise it constantly. it's a picture that hard to actually clarify, and a lot of research are being done in different aspects of this. So the question is, when I deal with a wave, I solve Maxwell equation, I solve acoustic wave equation, and the question is, when can I neglect them, right? When I do the wave, I carry the phase. That complex number there, right, is it gives me a lot of variation, which is good. If you want a variation, that's most beautiful. Okay, you can, but say, when can I neglect that, right? And let me go back to what I mentioned before. In reality, you do not have extended wave. You have wave packet, right? So in a material, right, I have an atom jiggling locally. It emits a time signal, a pulse, right? And there could be a pulse length over a certain amount of time, right? And also over a certain spatial extent. So this is a wave packet. Right, composes a lot of frequencies. And if, let's say, there is the frequency spread is delta nu. And in optics, there is definition of coherence length. And in fact, as a coherence is very extensive discussed in optics books. If you want to understand coherence, you should read that. And there's quantum coherence, there's classical coherence, and there's spatial coherence, there's time coherence. Okay, and here I'm given the simplest time coherence. So if I have a wave packet that has a frequency spread, then there is also corresponding space spread because they have propagated in different velocity. So this space spread is coherence length. This is of the order of delta, say delta nu. The speed of light divided by the spread, right? That gives you the length scale. So, yeah, physically, this wave packet also covers some length scale. And the space coherence is at 2 points whether the wave packets are correlated or not, right? And typically with a random thermal source, for example, I have vibration, atomic vibration here, another place, I typically just ignore this spatial coherence. The two vibrations are spatially uncorrelated. But there are other cases where they are actually correlated, okay? But say, what I actually had a lot of misunderstanding myself over this process, many years. But first, let's say I mentioned, if you recall, if I have wave packet, if I have a perfect interface, right? And it comes to the interface, and some of this will transmit it. And you can see that it's still the same packet, right? Transmitted, reflected. Some of this is reflected, right? So at that zero thickness at the interface, the reflection and incoming are spatial, it's correlated. This is the same wave packet. So you have to, if it's a perfect interface there, you have to use your wave mechanics to deal with. It's a wave, right? So that's a single simple interface. Then what about the film, right? So if I think about the film of thickness d, and my wave packet comes in, right? I'm looking at the tracing the same, Because if they are the same, if they overlap spatially, you have to include that phase addition. They interfere with each other. If they come from different wave packet, they are not correlated, because the one that emitted, say, in the next time step may not be correlated with the one that emitted by the previous time step, right? So two different wave packet, I don't care. I'm considering the one that somewhere coming from a source propagating inside the film and now reflected. So whether I consider interference or not, then this is the same wave packet, maybe different amplitude, but they come from the same parent, right? So if they spatially overlap, you have to include the interference. You have to use the wave superposition that we dealt before. So one of the criteria is, so if D is much larger than coherence length, if this is very large, the same wave packet, of course, at the interface, I have to use that Fresnel formula, which is a wave result. But once they are away from interface, most of the region in the film, like a window, this packet will not overlap. So you can just trace them as particles, trajectories. Forget about the phase, because you do phase, you get the same result, right? So that's one scenario. In fact, I thought this was the most scenario. When I was the first paper when I was a student, I wrote, a PhD student, I wrote, was on this problem. And I thought that that would answer the wave particle transition. And in fact, in optics, so there are two ways. One is the transfer matrix to calculate reflectance. The other is just completely ignore the interference and do retracing, energy bounce back and forth, right? But you look at the formula, it's very different. So I actually was just cook up a formula, and then then my advisor say, oh, you should look at theory. So I went to check. It turns out there is all those optical coherence theory, and I use the theory, and I say that's the transition. So this is where the demarcation come from. Film is thick, you neglect, say, interference. Film is thin, you don't neglect interference. Seems all very logical. But then years later, I realized this is a problem. Other people probably know this very well. But the problem is, if I have a black body which has a spread, and in fact, you can calculate effective spread. If black body has a, right, it's a peak, right? You say 0 to infinite of frequency, but you can calculate effective bandwidth of that 0 to infinite because it peaks around Wien's law, right? So, but see, when I calculate the multi-layer structure, particularly superlattice we mentioned before, Bragg reflector, right? Bragg reflector is a 1-to-1-to repeating structure, right? And it turns out that you really don't get this result. You say the limit, even it's very thick, you still get your wave result. You can never get the result where you neglect completely the interference effect. So I thought about this, and now the physical explanation is again the same parent. Say the wave packet came from the same parent that actually overlap. Why? If you say, okay, here I have a packet comes in, and they go into the first layer, and that packet and reflect once, refract to the second layer, reflect once, right? This is from the split from the same parent packet there. Of course, because of the time delay, I don't have overlap between this one and this one, right? Because this one traveled longer time. So when this wave packet coming into this layer, it's already, this one already gone out. However, but this one has a lot of reflection here, another reflection back, And that's coming from the same parent. And these two can spatially overlap. And hence, even though you have a very thick one, they can still interfere with each other. So your structure actually gave this packet a coherence. So you cannot completely just use the coherent length, simple coherence length, to neglect the wave effect. Okay? So that's say in lesson learned in optics. And the next lesson is the photon scattering, which we'll dive in the next lecture. And photon scattering, so when I have, say, lattice vibration, and they are typically 3 photon interaction process. So in this case, what I have is inelastic scattering. So now you have to look at the scattering. So inelastic scattering is when I have 1 photon omega 1, 2 photon comes in, and they interact, they form third photon, and the energy of the third is the sum of omega 1 plus omega 2. Right? Those kind of process pops up randomly in the solid, because photon propagate anywhere, they are not fixed. Right? So those processes are usually considered as phase destroying. So inelastic scattering typically, if your process is dominated by inelastic scattering, and that gives you the, let's say, the mean free path, the distance between those scattering events, right? And of course, say the scattering itself may involve phase superposition. But between one point to the other, the wave, once it scatters, it propagates as a packet. The next instant, it scatters to another direction as a completely different wave packet, because they lose their parent information. It's random. So in this case, I can consider the waves, I can forget about the superposition of waves between different scattered waves. So I treat them as particles, uncorrelated particles. So inelastic scattering is typically you can treat as a say particle if this process is dominant. But there's another process. For example, if I have say a solid or impurity atom in the material, and the wave comes in, whether it's an electron wave or photon wave, they comes in at 1 omega, they goes out at another omega, the same omega. They just change direction, right? This is a light, for example. Typically, when you have dust in the sky, the light comes in, they diffract to your eye. This kind of process, the particle position is fixed, right? But the scattering direction could be, depends on the solution. You have to solve the Maxwell equation. For that problem, it's classically called the Mie theory. Or you solve the electron atom, all those problems. So because this guy is fixed, so the scatter one actually have a fixed phase relation. Different direction, you have different fixed wave. So these are the elastic scattering. And typically, elastic scattering really does not destroy phase, right? Because say this position is fixed. It just got deflected different direction, may get a different phase. But this one has a fixed phase relationship. So then the question is, do I treat them as particles if this one is dominant? Turns out that here you got really complicated possibilities. For example, you have can have many particles in it, and you can have a wave comes in, and say scatter into here and scatter into here. And you could also have waves scatter back along the same path and completely cancel the incoming wave. So those kind of wave superposition is called localization. So if it's an elastic scatter, you can have localization. And you could also have where, because at least each one you can have complete pattern of scattering, even though the fix is different direction is fixed with regard to the incoming one. But when you consider many of them, spatially they are random enough, you actually can neglect those phase superposition. So in that case, you can go again into the particle picture. If it's a localization, you cannot. But in the other limit, you can neglect the phase. You just treat them as particles. OK. Here you will say, when I can do it. I can't tell you. It's very complicated. OK? And the idea of if you actually read, because you know we discussed several times the photonic crystal, right? And the photonic crystal, that concept, the name was coined by Yablowitz. But in the same year, there was another paper studying the same phenomena. That's by John Sanji. And he was studying the same structure, and he wants to look at when the wave gets localized. So there are completely different angles looking at the same problem. So yeah, photonic crystal is actually typically accredited to two people, Yablowitz and John Sanji. Okay. So you look at the different literature, it turns out in optics, people talk a lot of coherence. And of course, in electron transport, a lot of people also talk coherence. And one of the biggest problems with the quantum computing is how you can keep the wave phase. You don't lose the phase. You lose the phase, your superposition of waves is gone, right? So you maintain the phase coherence time. And if you read the literature, there are many different lengths. For example, there's this, I think it's a very thoughtless lens. Different length scales. And of course, there are diffusion lengths, all those. So talking about those transition picture, very, very complicated. And we have been studying heat conduction in superlattice. And recently, we think we have really found the evidence that there is a phase coherence contribution to thermal conductivity. And there is another very mysterious result on thermal conductivity of nanowires, where there are some rough nanowire people reporting way below what the classical size effect could predict. And now the paper being written, and some speculation whether localization is the reason or not. But there's really no strong proof. So doing theory, doing experiment in all those regimes are very difficult. OK. So given what I said, so you see this is an area that needs more research. You might be interested in doing it. But now I'm making the transition. I say I'm jumping from the case where I consider the phase of the wave, as I'm doing in this chapter, to the case in the next stage, I'm going to treat all those energy carriers as particles. I completely ignore the phase. Right? This is a different level of granularity. Remember when we talk about Einstein wave-particle duality, is waves is both wave and particle. It has momentum, it has a phase, right? But what I'm saying is that I'm migrating into a classical regime where I completely drop out the phase information. I look at trajectory of those particles. So this is where we're migrating to the next chapter, and chapter 6. So chapter 6 will start talking about the transport by particles. Okay, and let's start with a general equation. In this case, Liouville equation. So Liouville equation describe the particle in a system, how they move. And it's very general because let's suppose I have n particles in the system. And let's suppose each particle has, say, 2m, each particle 2m degree of freedom. And this degrees of freedom represent, for example, if I have x, y, z in Cartesian coordinate, translational degree of freedom, I will also have vx, vy, vz, right? So I have momentum, I have coordinate, space coordinate. Or if you think about angular, theta, phi, you have angular momentum. So 2m means if I have r, right, say r, the ith particle, I have r1 to r, say im. This is space degree of, say freedom. And correspondingly, I have p I1 and p momentum Im. So I have 2m, right? I'm going to use the notation. OK, my total number of degree of the freedom is 2n equals 2m times n. That's total number of degree of freedom. See, I have n particle in the system, 10 to the 23rd Avogadro constant. Right? If each particle is monoatomic, it's only doing translation. So I have 6 because the m is 3 for x, y, z, and the vx, vy, vz gives me 6. So each particle I need 6, and 6 times n gives me total number of degree of freedom. But I have, say, I use a generalized. So if I general this one, I have 2n. Say Rn and Pn, those are my generalized coordinate, right? So if capital N is one Avogadro constant, this is a 6 because I just explained 6n is my divided by 2 is 3n is a say space coordinate and momentum coordinate. Right? So this is a huge number, high order space. Right? And at each point, if I have one point in that space, I know the whole system because I know every particle's position and momentum. Right? So now you have to generalize your 3D to n dimension, and nobody can draw that, of course. And this is my phase space. So this one forms my phase space. Okay. And now if you recall, in chapter 4, when we discussed the generalized theory of statistics, we mentioned, now that I say you don't need to really, we're not to test it, as you say, right? but I did mention the ensemble concept, right? So ensemble is if I take a system, either isolated and or constant temperature and constant number of particles, constant chemical potential, right? So I take each quantum state. Rather than do time average, I do each quantum state is say ensemble is one system in my ensemble, right? So each quantum state now has one set of Rn, Pn, right? Because I know the position, I know the momentum of all the particles. So one set of Rn, Pn, and if I have many quantum states, I have many points. There are many points in my phase space, right? So in my phase space, now I can draw it. So I'm going to simplify my Rn, my Pn, right? I have in this ensemble, each point represent a quantum state of the ensemble in the phase space. Okay, and of course, now I have many, many particles in my phase space, so I can do density. I can do probability density, and so that I introduce the particle distribution function. So the Fn. So this one is the number of particles, and T, and Rn, Pn, right? This is the n particle, capital N. I have n particle in the system. Distribution function. And what it means is, if I know this distribution function, I multiply by the volume of this phase space in this near that point, Rn, Pn, and that gives me the number of systems in the ensemble having the coordinate Rn, Pn at time t, right? So this one is my n particle distribution function. Okay? So as my time evolves, right? Now I'm going to mix my time with the ensemble. As time evolves, the system state change, right? That means each of the ensemble will also evolve in time. Each of the system in the ensemble, right? But say, because each system starts with a quantum state, as time goes on, the two systems can never have the same quantum state, right? Otherwise, you go back, you will say, if they start with the same, you go back, it will time reversal, you will be the same. So, so what does that mean is this each point, as time goes, it forms a streamline. Now you can think about fluid mechanics, right? You form a streamline, and this streamline do not intersect. It's actually an incompressible flow in this n-dimensional phase space, 2 n-dimensional phase space. Okay, if it's an incompressible flow and the particle is conserved, you can write actually an equation of motion for this Fn, right? And Fn is incompressible, and if you think about this is if you gone through 255, 266, it derive actually the like a mature derivative, all those stuff. So you can do actually differential volume. You see what comes in, what goes out, what comes in, what goes out, right? And because it's incompressible, so at the end, what we have is the equation for this distribution function. What I have is df n dt. This is time, and then sigma I equals 1 to n, and say r time derivative. So I will do a dot. This is dr dt because I'm doing time evolution, and df n dr n plus I equals 1 to n, and p time derivative. No, so I should not do I. This is I. This is not n, because I'm doing summation over I. dp dfn d pi. And this is an incompressible flow. And this is essentially the Liouville equation. OK. Nobody solves it. It's hard to solve. Right? You have, if you think about degree of freedom, is 2n, the n is Avogadro constant. Right? But it's the start. And from here, the physics branch into two directions. And one is from here, one is the Boltzmann equation. Okay? And Boltzmann, how to go from a Liouville equation to Boltzmann equation, there are books, a whole book devoted to it. Many, many layers of say approximation. Okay? And we'll spend 3 chapters discussing Boltzmann equation. And then there is also the linear response theory. And if you have enough time, chapter line, chapter 10, chapter line is sort of start of a linear response theory. Boltzmann, of course, is way earlier than Einstein. And Einstein's, one of Einstein's motivation in his PhD thesis was, his PhD thesis was on Brownian motion. One is to use Brownian motion determine the atomic molecular size, one of these motivation. But another motivation is that Boltzmann equation is only applicable to dilute gas. Okay, so I said I can trade parallel electron, photon molecules, but I can't trade liquid, right? Liquid is not a dilute gas. And what Einstein started is trying to develop a parallel theory to Boltzmann. So he is actually, he laid the starting point of this branch, linear response theory. And if you do molecular dynamics, this is actually the, say you start from Liouville equation. You don't try to simplify it. You solve each atom. Right? Computer now becomes more powerful. So you can actually do your n particle problem, F equal ma. But say you have to know, you need to know the linear response theory. That's the foundation for all the analysis. And in fact, it's conceptually it's very easy, equal to do F equal to ma. But how to get into the understanding is where that's this theoretical foundation. OK, so this is the Liouville equation. And also there is a very interesting, if you go to, for example, talk about those, how the entropy, right, eventually come out of those equations is still very heavily debated, right? Because those most of those equations is time reversal. You put a negative time, it goes back to original point. But entropy is not a time reversal; it's time increasing. Right? So that's another, say, still very confusing point. So let's go from here to Boltzmann equation. We're not going to finish this. And Boltzmann equation is a tremendous simplification. And here we have in the say Liouville equation, I have an n particle distribution function. N is Avogadro constant. What Boltzmann equation does is a one particle distribution function, from 10 to the 23rd down to 1. That's a simplification. That's many order. That's why I say a lot of books written on it. Right? And the Boltzmann equation is defining the one particle. Now is Ft, R, and P. Right? Any particle that has a location R and P. Or maybe I can just write this is a, let me start with one particle rather than the TR1, P1, right? And then I generalize R1, P1 because I say it's just any particle, so I RP. And what it has is the average of the overall other, if I have 10 to 23rd particle, so I average over the all other 10 to 23rd minus 1 particles. So what I have is, in definition is I have the n factorial and minus 1 factorial. And that is averaging over all the other particles, right? So this is a Fn, but then I'm integrating over dr2 to drn and dp to dpn. You can say I'm averaging all the rest of the particle. I say this is my one particle distribution function. Okay? And because of this, now this particle, other than a system in the ensemble, right? It never interact with other systems in the same ensemble. It's parallel, incompressible, non-interacting. That's Liouville. Now I'm one particle in the system. In the system, it will interact, it will collide with other particles, right? So if you do your integration, averaging over the Liouville theorem, you get all the blob of the other particle. That's the one particle interacting with the other. So what I'll have in the equation is the Boltzmann equation is df. Now I do this f in general. I'll say df dt. I don't write 1 anymore. It's dr dt and delta r f, right? This r is generalized coordinate for one particle, and dp generalized momentum dt, and the gradient with respect to p F. This is one particle. I'm averaging over other 23 10 to 23rd particles. That averaging term is not 0. And I'm putting here, right now, just into a symbol. That's the interaction. That's my collision term of this particle with the rest. OK? And this is halfway to the Boltzmann equation. Right? So it's simply from 10 to the 23rd, a huge number, to one particle distribution function. And of course, dp dt, you can write f over m. That's a. And then this p could be changing to velocity. Because, say, that's a derivative, whether you write delta v f. So if dp dt is then times, because m, right? P is in the d in the denominator. P is mv. So you can write the m, 1 over m, or you can even write into the quantum form k, right? P equals hk, right? So it will be h bar times k. No, 1 over h bar, because this one equal also is, in terms of k, is 1 over h bar. So there are different ways to write this momentum term. But the most complicated is here, the interaction. And I will discuss this in the next lecture. That's a very complicated term. But what I want to drop to you is the Boltzmann equation is based on, if you know one particle distribution, the assumption, if you know one particle distribution function, you know all the other particle distribution function. And the reason is this molecular chaos assumption, right? So molecular chaos. And just to say, the particles do not really interfere with each other. They scatter, they interact, but say you know the distribution function of one particle, then you know all the n particles. So this is the n particle distribution function, T, Rn, Pn. That's what we wanted, right, in the lower equation. And molecular chaos is just, this is F1, T, R1, P1, times, right, the same T1, T, Rn, Pn. So if I know this distribution function as a general function of space and momentum, I know all the say n particle distribution function. So this is it's an independent. So you do have collision, but after collision, they forget where they came from. They lost the memory. And so molecular chaos. That's a fundamental in how you can get from the Liouville theorem equation to the Boltzmann equation. Okay. And just one more comment is, for example, Boltzmann equation, when you have dense fluids, it doesn't apply. So what the people had tried to modify is actually do two particles and consider finite size of the molecule. There's another equation called Unscock, which is a two particle distribution function. But the equation became very hard to handle. Not many people ever solved it. And so that's since the 60s, more effort were actually going into the linear response because the computer become available. People can do computational analysis and go response theorem. OK.